Hi everyone, I am Sania Kuller, and today I'll be talking about multiple test hypothesis correction using the Bonferroni correction approach. So again, if there's any questions you have along the way, please let me know. So it's one of the main methods that we use for hypothesis testing when we have multiple hypotheses that we're testing, and we have a lot of gene values as well. So it's a common approach that we typically use. So for instance, a common application is over here where, let me just share my screen now as well. So let's look here at the situation where we have a bunch of these different, mutations that take place. So there are about, 3,170 different mutations that have taken place. And these are BRCA. So BRCA refers to BRCA1 is, these are BRCA mutation in either the BRCA1 and BRCA2 genes. These are tumor suppressor genes, and these are related to breast cancer. So we want to look at these expressions for these number of different genes here. And we have, one group, which is BRCA1, and we have the other group, which is BRCA2. So what we've done here is we performed a two-sample t-test where we're comparing the, expression levels for each of these different genes here across, between the BRCA1 individuals and the BRCA2 individuals. So if you have mutations, in, BRCA1 or BRCA2 mutations, you're much likelier, to have a high risk of breast cancer. And we want to compare, the expression levels for these different genes over here, the 3,170 different genes. We want to compare the expression levels and see how those differ. So we perform something that's known as a two-sample t-test, where we're pooling together these samples, and we're pooling together these samples here for the BRCA2. So we're looking across these samples, here these samples, and then this other group of samples over here. And what we're trying to see is if there is a statistically significant difference in terms of the expression levels between, for a given gene like HK1A1. Is there a statistically significant difference for its expression for the BRCA1 individuals and the BRCA2 individuals here? That is what we're looking for over here. If there is a statistically significant difference between these individuals and these individuals for this gene. And then we're also doing it for this other gene here, then for this gene and this gene and this gene and this gene and this gene, where we're looking across the distribution here and we're comparing it with the distribution over here. We're seeing if there is a difference indeed. And then that is what we're doing with a two-sample t-test. So we're conducting a bunch of two-sample t-tests, and these are student t-tests that we're performing. And we are then getting, so often what you do for the two-sample t-test, it's typically given like this, where you're comparing the means between the two groups and, the sample means here and what you've gotten, and you're dividing by the sample size divided by N1 plus S2 squared over N2. So you're performing a two-sample t-test here with this information. Then what you're doing with the two-sample t-test is you're getting a p-value. Like, are these two groups, is this BRCA1 individuals with this mutation, do they have a statistically significant different p-value like for the expression for this HK1A1 gene than the individuals in BRCA2? Is there a statistically significant difference? And then, so we're doing this test multiple times for each of these genes. So that can lead to all sorts of results because we're doing multiple hypotheses. So what we want to do is we want to control for that. So we've performed this test, and then we have these results here where what we've gotten now is we get the p-values from these, we perform a two-sample t-test, and what we get is we get the set of p-values for each of these. So what we're going to do here, for instance, is we're going to say, okay, well, we performed the two-sample t-test, and the associated p-values that we've gotten are the following. So we've gotten the set of probability values as well, but we also have to sort them. So we perform the tests, we get our probability values, and then we sort those probability values from least to greatest over here. So you can see these probability values are then sorted. And each of these probability values corresponds to the two-sample t-test for each of those 3,170 different genes here. So it starts from 0 to 3169 because I was using Python to get this information. Now what we want to do is we typically use a value of 0.05. Then we reject the null hypothesis. The null hypothesis is saying that there is no statistically significant difference in gene expression for for a given gene between BRCA1 patients and BRCA2 patients. So that's the null hypothesis. The null hypothesis is that there is no statistically significant difference in gene expression for this one between these patients and these patients. That means that they're the same. And our alternative hypothesis is instead given by HA, which is, the alternative. And it says that instead there is a statistically significant difference. So what we see here often is for our null hypothesis, it's typically given by, that the mean would be the same. So what that means is that like the average expression according to the null hypothesis is that this is BRCA1 is equal to BRCA2, that their expression is the same. That is what this null hypothesis is. And the alternative hypothesis is instead of saying that there is a statistically significant difference. That is, these are not the same. BRCA1 is not the same as BRCA2. So that's the alternative hypothesis. So we have performed, for this testing, we have essentially, and credit goes to Professor Daifan Wang, for the slides from University of Wisconsin-Madison. So we're saying that there is a statistically significant difference in gene expression, like values for a given gene between these patients and BRCA1 and BRCA2 individuals. So these are our p-values, and I then sorted them. What happens is that we typically reject the null hypothesis if our p-value, so usually we use a p-value cutoff, if our p-value is less than 0.05, that means it's less than a 5% chance of observing this data that we got. For each gene, there's less than a 5% chance of observing the data that we got if the null hypothesis is true. Then what we would say is that, so, if there's less than a 5% chance of observing like this data and this data, like the distribution of this data, if the null is true, then we have evidence to reject the null hypothesis and say that the alternative is true. That means it's so rare for us to observe the data that we did if there's no statistically significant difference. So the p-value is pretty much, it's a probability of observing the data that we have if the null hypothesis is true. If this probability is less than 5%, we typically please reject the null hypothesis and instead accept the alternative hypothesis. That's what we would say here. So but the fact is that we're running this multiple times, the same two-sample t-test that we did. We're running it 3,170 times, and a two-sample t-test is a great way to compare between two groups, to do this testing. And you'll see here from the formula for the two-sample t-test that we are using mu1 and mu2. These are like the means that we expect. We expect these to be as close to 0 as possible because we expect it to be 0 under the null hypothesis. That the average expression, this is an average expression that we expect for this group versus the other group. We expect it to be as close to 0 as possible. That we expect the difference to be as close to 0 as possible because we expect the expression to be the same. So instead, we reject the null hypothesis And we would instead accept the alternative if the p-value is less than 0.05. But the issue of multiple test correction comes that the fact that we are performing this 3,170 times. So we need to correct for this. We have to then instead pool together those p-values. We have to use a family-wise error rate instead of 0.05. So that's the family-wise error rate is typically called FWER. And instead, we're going alpha of 0.05. This is our alpha. And we typically say if our p-value is less than 0.05, we reject the null. But the fact is that we're doing so many comparisons. And that's why we have to make some adjustment, because we're going to get a lot of these to be significant when they might not really be as significant. So it's a hypothesis correction that we need to do. See, like we have 75 out of 170 records that are found as significant, but they may not necessarily be significant. It's just the fact that we're performing so many of these two sample t-tests that we could get a lot of needlessly significant results, So it's better for us to do some testing correction here. So under the Bonferroni correction, we have a simplest approach where we choose a p-value threshold beta such that the family-wise error rate is less than or equal to alpha. So our alpha is 0.05, and we want a family-wise error rate that will be less than or equal to 0.05. So G is the number of genes or tests. So here we have 3,170 genes or tests. And for beta times G much less than 1, our beta should be approximately alpha over G. This is our threshold. So I'm going to kind of show you an example of how we would do it. So again, this is the Bonferroni correction formula here. It's the simplest way for testing for a multiple hypothesis. There are other ways, like there's Benjamini-Hochberg, and then there's the Story-Shebarani approach as well. There are multiple ways to test for this multiple hypotheses. And there are multiple hypotheses because we're testing the two sample t-test for multiple different genes. So this formula, let me bring it over here and show you guys that our goal is to select a family-wise error rate that is less than or equal to our alpha. Okay, so what our alpha here is we're going to set our alpha to 0.05. That's like the typical value that we're using. We're just going to adjust the typical, the typical is that we're going to, we reject the null hypothesis if the p-value is less than 0.05, where our alpha is 0.05. We're going to use the same thing here. And what we're going to do here is I'm going to set my alpha again to be 0.05. I'm going to say the number of genes or tests that we have is going to be 3,170. Then my beta threshold, which is what this is over here, is going to be alpha divided by my G. And when I take this cell here, 0.05 divided by 3,170, I get my beta threshold. And this value is approximately 1.57729 times 10 to the negative 5. So it's like you're adding on these 5 decimal points here. That's what this is. And our goal is to then, so what we're going to do is instead of reject the null hypothesis, if it's less than 0.05, we're going to reject the null hypothesis. So I'm going to carry this over. So what we're going to instead do, because this is multiple Bonferroni correction, we're going to have the same hypothesis, for sure, same hypothesis, guys. But what we're instead going to do is we're going to say, this is our alpha, but our beta threshold is what we're going to use. We're going to use this threshold. This is our beta threshold that we're going to use. And we're going to instead reject if the p-value is less than beta threshold. Then we're going to instead reject the null hypothesis. So it's like we've scaled our alpha by the number of tests that we're performing. And so instead, like for one test, we typically have G as 1. So alpha is in typical ways when we have G is just 1. When we just are running 2 sample t-test, our beta threshold is just the same thing as our alpha. It's just beta threshold is equal to you know, that is just equal to alpha divided by this. So it's equal to this. And this is just 1. So it's just equal to alpha. That's typically just all that it is. You know, it's G and then this is just alpha over 1, which is just alpha here. So that's what we do. And so instead of rejecting it when the p-value is less than alpha, we're rejecting it when it's less than the threshold. And this threshold is this value here times 10 to the negative 5. So how this works in action is before, when we were just using the example of 0.05 as our threshold, we got around, you know, like 75 of them that were significant. So under 0.05. But now we're going to use our cutoff of this. So let me copy this and let me just, you know, paste special so that we keep this value here. And I'm going to then take this value and I'm going to say that this is my beta threshold. Is this value over here? Let me just copy him over here and paste it here. So this is my beta threshold. So I'm going to use an if statement. If this value is less than beta threshold, I'll say it is significant. And I have a happy face. Otherwise, we say it is not significant. And we have a frowny face. So another thing for you to note is that this, I had sorted this from minimum to maximum here. So the values are increasing. So we should expect that like we would have significant, oh wait, I also have to, one sec, I also have to make this coded here. This is an absolute reference. So that means that it's all gonna stick. Okay, great. So this means that everything is this, I'm holding this constant as my threshold. So what we're going to observe is that this beta threshold under this value, we instead just have these 4 that are significant, statistically significant, whereas instead here we had about 75 values from before that were significant. So count is 75. So what happens is under the Bonferroni correction, we only get these 4 that are significant statistically. So if we look out over here, these are all the p-values between 0.000 and all the way between 0.01. These are all these values here. And then we zoom in a little bit, you know, from here, we can hone in from 0 to 48. We just zoomed in from the 0 to 95. So I just honed in on this window a bit more. And we just see that we have 4 values out of the 3,170 that are statistically significant under the Bonferroni correction. So the Bonferroni correction instead goes from the 75 that we found was significant down after multiple testing correction. Because we're performing 3,170 tests and we might just randomly get a lot that are significant when they truly are not, you know, just by chance. So that's what we are testing for here. And I sorted this from, you know, smallest to greatest. So we instead have that there are 4 that are statistically significant, and that's the 4 that there are. So you can sort the p-values, but again, the way that we found the threshold is we took alpha, we divided it by the number of genes, the number of tests that we're performing. And that's what we scaled it by. So typically, if we just have 1 test, then our threshold is just our alpha, not just the 0.05 that we're using. And we want to have a family-wise error rate instead of 0.05. That's what we are wanting. So we want our family-wise error rate to be less than or equal to alpha. So we're going to set this here, you know, our family-wise error rate at 0.05. And the only thing is instead we're using beta threshold as alpha divided by G. You can think of it as even over here, that we are rejecting it, the null hypothesis, if our like beta value is so it's 0.05, but if we do 0.05 divided by 1, then that's a kind of like our alpha that we're using. So the G is 3,170. This is our alpha over here. And, you know, we want to reject it if there is a statistically significant difference in gene expression. Otherwise, we want to retain the null hypothesis. And typically, this alpha is the same thing as our beta threshold. It's the same thing as beta threshold, where G equals 1. where the number of genes, where the number of tests that we're performing is just one. So after the Bonferroni correction, we just have these, and we can keep track of which genes those are, but we just have 4 that are statistically significant. So I just hope that this helps you. So please let me know if you have any questions on this. And there are other methods like that I can explain more later, but this is just one of the approaches for multiple test correction. So of course you would keep track, in reality, you would keep track of which p-values these correspond to. And that's what you would like find out which genes those are, and then which ones of those are statistically significant under Bonferroni correction. So we would go back and we would look here and find like which of those 4 those were. So for each of them, we would keep track of the p-values, like this. We keep track of the p-values that we get. And that's how that works. So yeah, please let me know if you have any questions at all. I'll be very happy to explain and to help with that. So yeah, just please write in the comment section or just reach out to me if you have any questions at all. Thank you guys so much.